Welcome to this video on integration by substitution. In this video, we're going to explain the theory and the method of integration by substitution. We're also going to demonstrate this method in some example problems and solutions. Sometimes we encounter integrals that cannot be evaluated with the standard integration formulas. Often we can evaluate these integrals by using this substitution method of integration. We can use this substitution method to rewrite an integral into a form that can be evaluated using the standard integration formulas. We can think of integration by substitution as the reverse process of the chain rule for differentiation. To help us to explain this, we're now going to quickly revise the chain rule for differentiation. We can use the chain rule to calculate the derivative of a composite function in the form y is equal to capital F of g of x. For example, here we have a composite function y is equal to capital F of g of x, which is equal to 2 over 3 multiplied by, open bracket, 1 plus x squared, close bracket, raised to the power of 3 over 2. When we look at our composite function, capital F of g of x, a component of this composite function is the function g of x, which is equal to 1 plus x squared. This function g of x is taking as its input the value x, and it's outputting a value equal to 1 plus x squared. Another component of our composite function is the function capital F. The output of the function g of x is being used as the input to the function capital F. And the function capital F is raising that value to the power of 3 over 2, and then it's multiplying by 2 over 3. When we have the output of one function being used as the input to another function, we refer to that as a composite function. We can express the derivative of our composite function as the derivative with respect to x of capital F of g of x. And we can calculate that derivative using our chain rule for differentiation as being equal to lowercase f of g of x multiplied by g prime x. Now we're going to explain these terms now. The term at the end, the g apostrophe x, we read this as g prime x, and this g prime x represents the derivative of our function g of x with respect to x. So g prime x, that's equal to dg dx, or the derivative of our function g with respect to x. You'll also see that we're now using a lowercase f instead of a capital letter F. Now this lowercase f represents the derivative of our function capital F. We can write the derivative of our function capital F as capital F apostrophe, which we read as capital F prime. This lowercase f letter, this represents the derivative of our function capital F. You may have heard the chain rule being referred to as the outside-inside rule. When we look at our composite function, capital F of g of x, we can refer to one of the component functions, capital F, as being the outside function. And we can refer to the other function, g of x, as being the inside function. Now the chain rule for differentiation tells us that we can calculate the derivative of the function capital F of g of x as being equal to the derivative of the outside function while keeping the inside function the same, multiplied by the derivative of the inside function. And that's our chain rule. And what we're going to do now is we're going to use this chain rule to calculate the derivative of our composite function. So the first thing that we want to calculate is the derivative of our outside function while keeping the inside function the same. Now we can work that out using the power rule for differentiation. Now here for this example, our power, our value of n, that's equal to 3 over 2. So according to our power rule for differentiation, we want to multiply by the power. So we're going to want to multiply by 3 over 2. And then we want to subtract 1 from the power. So when we multiply by 3 over 2, we get 3 over 2 multiplied by 2 over 3 multiplied by open bracket 1 plus x squared close bracket raised to the power of 3 over 2. And now we want to subtract 1 from our power. Now we can express 1 as 2 over 2. And 3 over 2 minus 2 over 2, that's equal to 1 over 2. Now our 3 over 2 multiplied by our 2 over 3, that's going to work out to be 6 over 6, which is equal to 1. So what we'll have is 1 times open bracket 1 plus x squared close bracket to the power of a half. So our 1 multiplied by those terms inside those brackets, that's going to just work out to be open bracket 1 plus x squared close bracket raised to the power of a half. Next we want to add our g prime x term. Now g prime x, that's the derivative of our function g of x with respect to x. Now the derivative of 1 with respect to x, that's going to be 0. And for the derivative of x squared with respect to x, here we can use our power rule again. So here our power is equal to 2. So we're going to want to multiply by the power and then subtract 1 from the power. So when we multiply by 2 and subtract 1 from the power, we get that g prime x is equal to 2x. Now a variable raised to the power of a half, that's another way of expressing the square root of that variable. So here we're going to take the square root of 1 plus x squared, and then we're going to multiply by 2x. And here we've just used the chain rule for differentiation to calculate the derivative of a composite function. We're now going to connect the chain rule with integration by substitution. In our previous example, we started with this function, the composite function capital F of g of x. Now, in our previous example, we calculated the derivative with respect to x of this composite function, capital F of g of x, using the chain rule for differentiation, which is shown here. In that previous example, we calculated that out to be the square root of 1 plus x squared multiplied by 2x. To explain integration by substitution, we're now going to introduce antiderivatives. An antiderivative of a particular function is another function whose derivative is that particular function. This function, which is currently highlighted in red here, this function, previously we calculated that this is the derivative of this other function which is now currently being highlighted at the top of the screen. Now, in our previous example, we differentiated this function at the top of the screen with respect to x, and we calculated that the derivative of this function at the top of the screen, that is this particular function currently being highlighted. So that makes this function at the top of the screen the antiderivative of this function, which is currently being highlighted. We're now going to introduce integration. As shown here at the top right hand side of the screen is the indefinite integral of the square root of 1 plus x squared multiplied by 2x with respect to x. In order to evaluate this indefinite integral, our first main step is that we want to try to find an antiderivative of this function which we are integrating. And then once we've found an antiderivative, we add plus c, and that's our set of all antiderivatives of that function. And we would have then evaluated our indefinite integral. Now, similarly, shown here at the top right of the screen now, we have the definite integral from 0 to 1 of that same function with respect to x. Now, in order to evaluate this definite integral of that same function with respect to x, for our first main step, we're trying to find an antiderivative of that function. And then once we've found an antiderivative, we do not add plus c. Instead, to evaluate the definite integral, we then evaluate over the limits of integration, which here are from 0 to 1. We can usually use a standard integration formula to find an antiderivative. But if we can't, if the function which we are integrating does not match up with any of our standard integration formulas, and if our function is structured like the end result of a chain rule differentiation calculation, then we can instead reverse the chain rule process by substituting terms and then integrating. Now, this gives us another way to evaluate an integral in examples where we can't use standard formulas. Now, previously, we've established that this function shown here at the top left of the screen, capital F of g of x, that this is an antiderivative of this function, shown here highlighted, the square root of 1 plus x squared multiplied by 2x. Now, over here at the top right hand side of the screen, we're trying to evaluate the definite integral of the square root of 1 plus x squared multiplied by 2x with respect to x. Now, our first main step is that we're trying to find an antiderivative of that function. Now, our function doesn't match up to any of our standard integration formulas, but it is structured like the end result of a chain rule differentiation calculation. Now, that square root of 1 plus x squared, that's a composite function of the form f of g of x, where g of x is equal to 1 plus x squared. And that 2x, well, that's the derivative of our function g of x, g prime x. So our function which we are attempting to integrate at the top right hand side of the screen, it is indeed structured like the end result of a chain rule differentiation calculation. It is, in fact, it is the answer, it's the result which we got in our previous example. So we can't match up this function to any of our standard integration formulas, but because it is structured like the end result of the chain rule, what we can instead do is we can reverse the chain rule process by substituting terms and then integrating, and by reversing that process we arrive at a antiderivative. Now this gives us another way to evaluate the integral. We're now going to explain the method of integration by substitution step by step. This method can be used in the most straightforward way on functions in the form of y is equal to f of g of x, g prime x. Now the substitution method has three main steps. As shown here at the top left of the screen is the indefinite integral of f of g of x, g prime x dx. For the first step, we substitute the variable u for the function g of x, and we substitute du for the terms g prime x dx. When we substitute the variable u for the function g of x, we get the indefinite integral of f of u. And when we substitute du for the terms g prime x dx, we get the indefinite integral of f of u du. So after doing this first step, what we've been able to do is we've rewritten our function into a form which should be easier to match up with the standard integration formulas. Now for the second step, we evaluate the integral by finding an antiderivative capital F of u. So here we're attempting to match up our function f of u to the standard integration formulas. Now if we're able to find an antiderivative, we then have capital F of u and we add plus c. And this is our set of all antiderivatives in terms of the variable u. Now for the third step, we substitute the function g of x back in, replacing the variable u. And we get our antiderivative in terms of the function g of x instead of being in terms of u. So that gives us our set of all antiderivatives, capital F of g of x plus c. And that's our method of integration by substitution for an indefinite integral. Now, this method works because capital F of g of x, that function, is an antiderivative of f of g of x, g prime x. When we evaluate the integral of a function with the form f of g of x, g prime x, we're trying to find an antiderivative of that function in order to evaluate the integral. Integration by substitution can be used to find that antiderivative, capital F of g of x, and evaluate the integral. It's useful to note here that this method currently shown on the screen is the substitution method for evaluating an indefinite integral. I'd like to briefly mention here that a substitution method can also be used to evaluate a definite integral. This involves some small differences which I'll briefly describe now. To evaluate a definite integral by substitution, we can first evaluate the indefinite integral instead, using the substitution method shown on screen. Once that is complete, we'll have our set of all antiderivatives of our function. We can then use an antiderivative from this set of all antiderivatives of the function to evaluate the definite integral over the limits of integration in the normal way. I'll create an additional video describing the substitution method for definite integrals, and I'll put a link to that video in this video's description below. We're now going to demonstrate integration by substitution in an example problem and solution. Shown here at the top left hand side of the screen is the indefinite integral of the square root of 1 plus x squared multiplied by 2x with respect to x. In order to evaluate this integral, our first main step is we want to find an antiderivative of that function which we want to integrate. This function doesn't match any of our standard integration formulas. So we check if the function has the form y is equal to f of g of x g prime x. The square root of 1 plus x squared, that's a composite function in the form f of g of x, where the function g of x, that's equal to 1 plus x squared. G prime x is the derivative of the function g of x with respect to x. We've worked out previously that the derivative of 1 plus x squared with respect to x, that's equal to 2x. When f of g of x is equal to the square root of 1 plus x squared, f of g of x g prime x is equal to the square root of 1 plus x squared multiplied by 2x. When we look at our function at the top of the screen which we want to integrate, this function does indeed have the form f of g of x g prime x. This makes it a good candidate for integration with the substitution method. We're going to attempt that now. For our first step, we want to substitute the variable u for the function g of x. And we want to substitute du for the terms g prime x dx. We have the function g of x, that's equal to 1 plus x squared. So we want to set 1 plus x squared to be equal to the variable u. We also want to set du to be equal to g prime x dx. We have from earlier that g prime x, that's equal to 2x. Now, making the same change to both sides of the equal sign, g prime x dx, that's equal to 2x dx. So we want to set this to be equal to du. Next, we're going to substitute these terms into the integral. So we have our indefinite integral of the square root of 1 plus x squared multiplied by 2x with respect to x. And we want to substitute the variable u for 1 plus x squared. When we do that, we get the indefinite integral of the square root of u multiplied by 2x with respect to x. And then when we substitute du for the terms 2x dx, we get the indefinite integral of the square root of u with respect to u. And that's the end of our first step. Now at this point, what we've been able to do is we've rewritten the integral into a form which we can evaluate with the standard integration formulas. For our second step, we evaluate the integral with respect to u. So far, we have the indefinite integral of the square root of u with respect to u. We can also express the square root of u as u raised to the power of 1/2. Now, when we make that change, we get the indefinite integral of u raised to the power of 1/2 with respect to u. This matches one of our standard integration formulas. This formula is now shown on the right hand side of the screen. This formula says that the indefinite integral of x raised to the power of n with respect to x, that's equal to x raised to the power of n plus 1 divided by n plus 1 plus c. We can make this formula a little bit easier to use with our example on the left hand side of the screen by rewriting it in terms of the indefinite integral of a variable u raised to the power of n with respect to u. When we do that, we have the formula saying that the indefinite integral of u raised to the power of n with respect to u, that's equal to u raised to the power of n plus 1 divided by n plus 1 plus c. We're now going to apply this formula to our example on the left hand side of the screen. Now, in our example, our value of n, that's equal to 1/2. So to start off with, we want to work out what u raised to the power of n plus 1 is. Our value of n is 1/2, so we're going to have u to the power of 1/2 plus 1, so that's u to the power of 1/2, which we can express as u raised to the power of 3/2. Then we want to divide by n plus 1, so we want to divide by 1/2, which we can also express as dividing by 3/2. So we do that now, and then we add plus c. And this is the set of all antiderivatives in terms of the variable u. We can simplify this a little bit further by applying our rule for dividing by a fraction. When we do that, we get 2/3 multiplied by u raised to the power of 3/2 plus c. And that concludes our second step. So far we have the indefinite integral of the square root of u with respect to u is equal to 2/3 multiplied by u raised to the power of 3/2 plus c. For our third step, we want to replace the variable u with the function g of x in the result. Now we have that the function g of x, that's equal to 1 plus x squared, and it's also equal to u. Now we want to replace the variable u with 1 plus x squared. Now when we do that, we get 2/3 multiplied by open bracket 1 plus x squared close bracket raised to the power of 3/2 plus c. And we've successfully evaluated our integral using the substitution method. That's the end of our third step, the end of our final step. And that concludes this example. We can perform integration by substitution in the most straightforward way when the function we're integrating takes the form f of g of x, g prime x, such as in our previous example where we integrated the square root of 1 plus x squared multiplied by 2x. Often, we can also perform integration by substitution on functions that don't take on the exact form of f of g of x, g prime x. Now we can do this by adding an extra step, as we're going to see in the following example. In this example, we want to evaluate the following integral, the indefinite integral of x sine x squared dx. The function that we're integrating is x sine x squared. Now, this function, it doesn't match any of our standard integration formulas. So we check if the function has the form y is equal to f of g of x, g prime x. Looking at the function that we want to integrate, sine x squared, that's a composite function in the form of f of g of x, where g of x is equal to x squared, and the function f, that's taking the sine of g of x, where g of x is x squared. G prime x, that's the derivative of the function g of x with respect to x. We can calculate that out to be 2x. When f of g of x is equal to sine x squared, f of g of x g prime x, that's equal to sine x squared 2x. Looking at the function that we want to integrate x sine x squared. So our function, it doesn't take the exact form of f of g of x g prime x, because f of g of x g prime x, that's equal to sine x squared 2x. In this example, our function differs by a constant value from the form f of g of x g prime x. The function that we want to integrate, it differs from the form f of g of x g prime x by a factor of 1/2. In situations such as these, where we want to integrate a function and it doesn't have the exact form of f of g of x g prime x, but it does differ from it by a constant value, well, in those situations, we can still perform integration by substitution by adding an extra step. We're going to demonstrate that extra step in this example. Initially, we still proceed as normal in working out our u substitution for the function g of x. So we're going to substitute the variable u for the function g of x. So we're going to set x squared to be equal to u. And we still equate du to be equal to g prime x dx. Now, if we look at our g prime x equation, if we make the same change to both sides of the equal sign here, we get that g prime x dx, that's equal to 2x dx. And we set this to be equal to du. Now, normally, if the function that we are integrating, if it did take the exact form of f of g of x g prime x, then we would be seeking to substitute du for 2x dx. But when we look at the function that we're integrating, we don't have 2x dx. We have x dx. Now, this is where we do our extra step. We take our equation, 2x dx is equal to du. Now, what we do here is we calculate what x dx is equal to in terms of du. Now, we can do that using our equation at the bottom right hand side of the screen by dividing on both sides of the equal sign by 2. When we do that, we get that x dx, that's equal to 1/2 du. And this we can substitute into the function that we want to integrate. We can substitute 1/2 du for x dx in our integral. So to summarize our extra step, we adjust our du equation by a constant value, which will allow us to complete this substitution. Now at this point, we have our substitutions ready. We're going to substitute a half du for x dx, and we're going to substitute the variable u for x squared in our integral. So we're going to do that next. We want to make the following substitutions. We want to substitute the variable u for x squared, and we want to substitute 1/2 du for x dx. When we substitute u for x squared, we get the indefinite integral of x sine u dx. And when we substitute 1/2 du for x dx, we get the indefinite integral of sine u 1/2 du. At this point, we can use the constant multiple rule for integrals to move the 1/2 outside of the integral. When we do that, we get 1/2 times the indefinite integral of sine u du. At this point, we've rewritten our integral into a form which can be evaluated using the standard integration formulas. We can do that using the formula currently displayed at the bottom right hand side of the screen. This formula says that the indefinite integral of sine kx dx, that's equal to minus cos kx divided by k plus c. We can make this formula at the bottom right of the screen a little bit easier to use with our example at the bottom left of the screen by rewriting that formula for a variable u. And when we do that, we get the indefinite integral of sine ku du, that's equal to minus cos ku divided by k plus c. In our example at the left hand side of the screen, our value of k, that's equal to 1. So when we make that change to our formula at the right hand side of the screen, we set k is equal to 1, and we get the indefinite integral of sine 1u du is equal to minus cos 1u divided by 1 plus c. 1 times a variable, that's equal to a variable. So we can change the 1u terms to u. And cos u divided by 1, that's equal to cos u. So when we make that change, we get that the indefinite integral of sine u du, that's equal to minus cos u plus c. When we apply this formula to our example at the left hand side of the screen, we get that 1/2 times the indefinite integral of sine u du, that's equal to 1/2 times minus cos u plus c. Now when we multiply that out, we get minus 1/2 cos u plus c. Now for our next step, we substitute our function g of x back in for our variable u. So we're going to replace u with g of x, which is equal to x squared. And when we do that, we get minus 1/2 cos x squared plus c. And here at this point, we've finished evaluating our integral using the substitution method. And this concludes this example. So to summarize, in this video we've explained the method of integration by substitution. This method can often be used to evaluate integrals which cannot be evaluated with standard integration formulas. We've also demonstrated integration by substitution with some example problems and solutions. If you found this video useful, please subscribe to the channel to receive more content. Thank you very much for watching this video, and see you next video.